All right, I want to talk to you a little bit today about some of the work that we are doing, as well as some of the collaborators in COPE in the area of energy storage and conversion. And I've heard a couple comments earlier today about chemistry and how chemistry goes a long way in engineering. Well, I'm an engineer, and engineering goes a long way to making devices a reality. So I want to come and talk a little bit more about some of the things that we're doing in terms of looking at device physics, but also looking at the packaging and making devices reliable so that it can actually reach the marketplace. And so the first aspect of this, some of this has been talked about already in terms of the focus of COPE, in terms of looking at organic photovoltaics. And so in general, in terms of the power conversion devices within COPE, we are looking at organic photovoltaics, where we're looking at even devices that have all polymer electrodes, which this is led by the Kipling Group and published in Science. We are looking at light emitting devices. I won't talk about those today per se. But beyond what we're looking at in terms of the organic electronics, we are also looking at other power conversion devices, things such as supercapacitors, using some of our organic materials in power inverters for hybrid electric vehicles, as well as using carbon nanotubes for electrodes in lithium-ion batteries. And so I'll talk a little bit about some of these aspects. So we'll cover, say, the traditional organic electronic areas as well as moving outside. And the way that we're doing this within the center is through a collaboration between scientists and engineers to have a strong group that's looking at materials development and material synthesis, as well as device innovation, as well as looking at the reliability and engineering aspects towards the lifetime overall. And so the first aspect I'd like to talk about is looking at dye-sensitized solar cells. And so this is some of the work that's been done in the Reynolds Group in chemistry, and sort of looking at the comparisons between organic photovoltaics and dye-sensitized solar cells. If we look at the organic photovoltaics, we basically have light that comes in that creates an exciton, and sort of this general model is to look at sort of a charge transfer step, as well as another step where we have charge collection at an electrode, or charge transfer over to an accepting molecule, such as PCBM, as shown here. And so if we look at a dye-sensitized solar cell, we sort of have a similar step where we have an exciton that's created, and we have a charge transfer step where the electron goes over to the titanium dioxide. And so what we want to do is actually look at this particular process and how we can maximize this process or engineer this process so that we increase the efficiency of dye-sensitized solar cells. And so in the Reynolds Group, what they're looking at are the creation of this toolkit where they can manipulate this charge transfer process by developing molecules that have electron deficiency, molecules that are electron rich, as well as a set of linker molecules. And by understanding these, they can put these together, and sort of the filter here in terms of the molecules they'd like to have come out, they're looking at things such as the redox chemistry, the optical properties you'd like to have, the energy levels so that you can match these with electrodes, as well as the processability. So things like surface processing, solution processing, I should say, and also surface absorption onto materials like TiO2. And so by looking at all of these factors, they can come up with a number of different molecules in which to tailor the operation of the dye-sensitized solar cells. And so in this particular case, again, just as a quick reminder, what we're doing is we have light that comes in that is going to be able to create an exciton. We're going to have this electron that's going to be transferred to our TiO2. And as the current flows through the circuit, we'll actually have electrons that come back through the electrolyte and replenish the dye molecule here. And so in a general sense, it's sort of analyzing our solar cells. We're looking at things like the fill factor as well as the power conversion efficiency. And so in their group, they are looking at a number of different molecules, molecules that are thiophene-based, benzothiodiazole-based, as well as isoindigo. And so with these different materials, what you'll notice is that if we look at a material like isoindigo, it has a lower band gap, so it has an absorption over a larger range of this particular spectrum here. So we're looking here basically at the visible light spectrum. And then you have a mid-band gap polymer, the benzothiodiazole. And then you have a large band gap polymer, which is the thiophene base. So we can look at these to see how they behave in terms of the efficiency of the solar cell. And this particular slide shows that particular outcome with these molecules placed on TiO2. If you look at the large bandgap molecule here, you'll see we have a power conversion efficiency of about 2.5. When we look at the mid bandgap polymer, we're up to about 6.4%. And with the Isoindigo, we're at about 3.4%. And if you look at the incident photon power conversion efficiency, then what you're looking at here is that the reason why this mid bandgap polymer is slightly better is because the incident photon conversion efficiency is higher over this particular portion of the incident spectrum as opposed to the small bandgap polymer. So it gives it the higher power conversion efficiency. But nonetheless, there is a methodology and a toolkit here to create these polymers so that we can play around with or engineer this particular charge transfer process to try to improve the overall power conversion efficiency of dye-sensitized solar cells. Some of the other aspects that we're looking at in terms of the reliability and the packaging of organic photovoltaics and other organic electronic devices is through the creation of ultra barrier films. And so it's widely known that a lot of these materials are susceptible to exposure to the environment. And so we've utilized recently a lot of atomic layer deposition to create oxide barriers. Some of these oxide barriers are monolithic films. Some of them contain a number of different layers, so we're mixing materials together in order to create ultra barriers where we can package devices, which we've demonstrated in the past, that show very low or very little change in the overall power conversion efficiency over the period of several months. And so this is a shelf lifetime analysis. And in addition to this, more recently we have been working with outside companies to look at things like flexible glass. So here now the issue is not necessarily making an ultra barrier, but it's how do you process on these particular structures. There's a little bit of an issue of fragility. So if anyone has actually worked with these, you'll notice that while they're showing nice pictures here in terms of the ability to flex these devices or flex these substrates, they are difficult to handle. And so how do you go about doing the sealing process in order to protect your devices? So we are doing some work to compare the ability to process on these particular substrates as opposed to having your normal, say, polymer-based substrates with the ultra barriers. So I won't talk a lot about the development of the ultra barriers and the application to OPV, but I do want to show some additional things that we've been able to do more recently. And so one of the things that we're starting to do is look at the application of these ultra barriers in harsh environments. And so in our case, we're putting these in environments that have relatively say high values of humidity, or actually putting them in aqueous solutions. And so this is actually a case where we're using zinc oxide as a sensor. If you put zinc oxide in water, it will basically dissolve. It will corrode. And so we're using zinc oxide that's coated with a layer of aluminum oxide, which is a common barrier film. And if you leave this in water over a period of days, you will notice that the zinc oxide is detected by photoluminescence. The peak from the zinc oxide will disappear. But there are a number of other oxides you can actually add to this where it gives you very, very nice stability. So we're looking at combinations of materials that will allow us to have survivability in these harsh environments. More recently as well, we've looked at some electronic devices, and again, this is a different combination of ALD layers that we put on top of our electronics. We're looking at electronics that have topography, and so we want to have nucleation that is consistent and good over a number of different materials. And so this is actually a commercial LED that we've purchased. We've applied our coatings, and these LEDs are actually now operating not only in just water, but also in saline solutions. And so we can leave them there, and the ALD coating actually protects them quite nicely. Interacting with the group at Utah, we have some capacitive devices that we place our ALD coatings on top of, and this shows the impedance spectrum as a function of frequency in terms of showing the quality of the coating. And some of these devices have been operating for more than 30 days in saline solution, also showing very, very low leakage current. So again, we're looking at not only just the creation of ultra barriers, but barriers that could withstand very, very harsh environments. Another aspect to looking at the survivability or the reliability of devices, when we start talking about flexible organic photovoltaics, OLEDs, or other types of electronics, we want to understand how some of these critical barrier films or some of these critical oxides we deposit by ALD, how well do they hold up in terms of flexural applications. And so the main issue that a lot of us have in terms of concern is the cracking of some of these oxide layers. So we'd like to understand what is the strain to failure, and what are some of the aspects of the processing that will lead to different types of, different levels of strain to failure. In addition to that, we also want to understand what is the adhesion in the devices. Are there critical layers that will actually separate if we are to flex this or apply a certain amount of mechanical energy or strain to these particular interfaces? And so we do this by using a mechanical test system where we place the device of interest in between two silicon substrates, and we'll actually peel it apart using something called a double cantilever beam technique. And there's something that we utilize to quantify this, which is called the critical strain energy release rate. This just basically says how much energy does it take to propagate a crack or to separate this particular interface of interest that we're looking at. And so we can quantify this. So the general gist here, of course, the higher that energy, the better it is for us in terms of mechanical reliability. And so we've applied this to inverted organic photovoltaic devices, and so this is one that's based on P3HT PCBM. We've done some other materials as well. And so this is an inverted cell that has a zinc oxide and a moly oxide interface here. And when we apply this, where we do mode 1 tension, we pull this apart. We can do XPS analysis of the surfaces after they've separated, and we can see here that it is separating here near the moly oxide P3HT PCBM interface. And so that is the weak link in this particular material system. If we change this to polymer contact, so if we go to P.PSS, what we will see is that, let me just back up. So the strain energy release rate here is about 0.4 joules per meter square. If we go to P.PSS, we'll actually see this value drop. So we actually see that there's a detriment to going to some of these polymer films if you don't process it correctly. And so one of the things that we have seen in our work is that, yes, there is hope. You can actually do annealing of these interfaces, and they will actually increase in strength. You can also do some other pre-processing. And so this is an area still of active research to understand how to improve this particular interface without damaging the overall performance of the organic photovoltaic. And so beyond looking at just the organic photovoltaic, when we start looking at these oxide barriers, this is one particular case where we're looking at titanium dioxide as a barrier film. And here we're strictly looking at the strain to failure. So this is a film that is about 10 nanometers in thickness versus a film that's about 30 nanometers in thickness. And when we look at titanium dioxide, there is something called the critical thickness, where beyond that you don't really get much additional benefit in terms of the water vapor transmission rate or the barrier performance. So from a manufacturing point of view, you want to make this as thin as possible, but it's still not clear what does it do to the mechanical properties. So if we look at a 10 nanometer thick film, you can see if I strain this now in tension to 1% strain, I don't detect any cracks in the film. If I go to 1.5% strain, you see the parallel cracks that actually form here. If I go to a 30 nanometer thick film, you can see now at 1%, I have quite a few cracks in the film. And so there's a strong thickness dependence to the crack driving energy in these particular films. So this also states that not only do you want to have the film thin, so from a manufacturing point of view, but you also want to have it thin from a mechanical compliance point of view or a mechanical reliability point of view. So we want to look at further studies that we're currently doing right now, looking at how underlying films or surface treatments, pre-treatments, the smoothness of the film will impact this onset cracking strain in the films. But overall, through we've looked at aluminum oxide as well as titanium oxide, and we see both this particular effect. You see a shifting of the onset cracking strain with film thickness. Moving beyond these aspects in terms of the packaging of organic electronics, we've also worked on thermal energy storage aspects. And so in this particular case, one of the things we'd like to do is use latent heat thermal energy storage aspects, where in most cases people are using things like paraffin wax in order to melt, store thermal energy. You would actually have this inside of a particular structure that is insulated, so that way you could store it for later use. What we've been able to do is address the problem that paraffin waxes have thermal conductivities that are very, very low, so it takes a long time to thermally charge and thermally discharge. It's the particular system. So we can add something called compressed expanded natural graphite. So basically, this is a very simple system. You buy this intercalated graphite film sheets, and you actually expand it using microwave energy. and then you use that like a sponge to soak up the paraffin wax. And what you'll find is that we can go from a material that has a thermal conductivity that is less than 1 watt per meter K to something that's on the order of 10, all the way up to about 25 watts per meter K. So now you're getting into the range that you have a material that's as thermally conductive as stainless steel, but it has only about a 15% drop in the overall thermal storage capacity as compared to pure paraffin. And so we've also used some additional augmentation by mixing in graphite flakes, where we use octadecyl phosphonic acids that will actually stabilize these materials in suspension. So this is 5 weight % ODPA. What we do is we hold the material in the liquid state, and if you don't have this ODPA inside, you'll see that the graphite will settle. And this hasn't settled over, I think, a 15-day period of being in the liquid state. So these particles are about 15 microns in diameter, so fairly large. And so it's a fairly stable system. And we're currently looking at the utilization of these in heat exchangers so that these will act as thermal batteries for storing waste heat energy for providing hot water to buildings. In another application, again, moving beyond the organic electronics, we start looking at devices such as hybrid electric vehicles. One of the biggest challenges in developing hybrid electric vehicles is actually developing more efficient power energy converters, or power inverters. And so there's a push right now to move to materials such as gallium nitride, so you can basically shrink the size of these power inverters by a factor of at least 5. The issue here is that when you do that, you also go up in power density, and so now you have devices that can, say, withstand 200 to 250 degrees C operating temperatures, but now you have to have thermal materials that can also handle not only the larger heat loads, but handle those particular applications. And so we're looking at materials such as carbon nanotube thermal interface materials to go into these applications. In addition to this, Baratunde Kola has also developed some very unique thermal interface materials that can also be used to address various aspects of this particular problem. And so I'll show some of those now. And here, the basic concept here is that if I have a chip that's generating heat, the heat has to flow out to the environment. And so one of the ways that we'll do this is that this particular blue layer right here is my chip. It will flow through a number of interfaces and go out through a heat sink that we normally see. And then it will also flow down into a circuit board and go through some other contacts and spread out and go out to the environment, usually through either a liquid cooling path. Here is using air cooling. But the major issue here is that if we have very, very large heat fluxes, we have to have very, very good materials here in order to lower the contact resistance between the chip and the next layer. And so these are the issues that we're trying to address using thermal interface materials by having very, very low interface resistances in areas where we have very, very large heat fluxes. And so in this work, Professor Kola has come up with a very unique way developing polythiophene nanotube arrays. So typically you think of polymers as having, again, low thermal conductivities, but through the creation of these polymer nanotube arrays, he's able to get, very similarly to what Seth showed earlier with the carbon nanotubes, very, very large contact areas. Through having these polymer arrays, he can actually grow them, place them on these metal lids, where you may consider this as being the metal lid that goes over the top of the device. And so it provides a nice conformal and soft contact to this particular device. And here, showing through controlling the electropolymerization, he can control sort of the size of these and the shapes of these particular arrays that he's having grown on this particular surface. And in addition to that, excuse me, I went too far. And one of the things I told Bara is that he said that I could present his slides, and I said it would probably go better if he presented them, so I think it holds true. But here we go. So here are the polymer nanotubes, and here's the interesting thing. If we look at the current technology in terms of thermal greases, where the total thermal resistance for that particular interface is at this time, you can see that it's somewhere, say here, between about 18 to 25 millimeter square K per watt in terms of the thermal resistance. And you can see where these polymer nanotubes are actually performing. So they're outperforming the commercial thermal greases that are used in these applications. And in addition to this, you also have very, very nice compliance by using these polymer nanotubes. So that allows you to put materials together to have different coefficients of thermal expansion without transferring a lot of stress to the die, which can actually be detrimental to the performance of the die. So with that, I'm I guess, a little bit behind the scheduled lunch, but trying to catch us up. But the main thing here is that we have a wide range of materials advancements, also looking at device design and device characterization methods that allow us to mix and match technologies to help the advancements of things such as dye-sensitized solar cells, OPV, as well as technologies that move beyond, say, the traditional view of organic electronics. So some of these things in terms of using phosphonic acids, using some of these ALD barrier coatings, we're now moving them over to, say, the power electronics arena. We've recently had discussions on that, as well as some other future technologies. And so we can pull from COPE and also to advance or affect other areas. And I would like to say that quickly, the diverse background of the researchers that we have in COPE and the discussions that we have amongst researchers and other students, basically that's the catalyst that allows a lot of this to happen. And I'd like to also acknowledge funding sources, NSF, Department of Energy, and DARPA, as well as the collaborations with the University of Utah for some of the work that I showed you with the LEDs and capacitors. Capacitors. Thank you very much, and if you have any questions, I'd like to answer those now.